Thanks everybody for joining this evening. So my name is Dor. I'm co-founder and CEO of Scylla. And along with me, I have Glauber Costa, one of our best engineers, ninja developers, a person who I'm trying to get his job. And we'll see if I'll manage to succeed eventually. So this talk is about our journey with Scylla, developing a database, an NoSQL database. And it's particularly one that we started as a re-implementation of Cassandra. There is a lot of things of where to go with the database. And as you may know, Cassandra, the database that we're trying to displace, is implemented in Java. We implement things in C++. This talk is pretty technical, and I'll try to show you through our journey of what are things that we had to do way beyond C++, and it's not just a language thing, although it's highly important. We have the Scylla stickers. This is our project mascot. It's open source project, and have these stickers on board. So those of you who want sticker, Glauber is giving them away for $1 each. Glauber, don't forget to charge. So the agenda is the following: a long introduction for NoSQL. If you don't know what NoSQL is about, then you were living in a cage or somewhere else. Some about Apache Cassandra, which the database that we're trying to displace. But we're not just trying to displace Cassandra, we're trying to provide much broader database and deal with many more workloads, do things that even go beyond what traditional databases do, not today, but in the future. So this talk won't be just about Cassandra, so I'll speak about general Cassandra background, and later on about Scylla, what we have today with the database, how it works. We will invest a lot of time for the internals, and we'll speak about workload conditioning, which is a set of algorithms that we used in order to provide not just great performance, but consistent performance. And later on, we'll wrap up. So without further ado, what's wrong with the picture? What's wrong? Too much hardware. Yeah, so that's right. Initially, it looks to me like way clearer, and I didn't attend such a nice, good-looking data center, but indeed, too much hardware. When we started this database, is about actually, we started this company and we've done something else, and we had to pivot from different reasons. That it's interesting story by itself, but I won't describe that too much in this session. One of our initial ideas before we started the previous original idea was, let's implement a database friendly for SSDs that will be super fast. And we didn't pick this direction because we thought there are so many databases, surely they're doing a good job. But apparently it's not the case. And at the time that we stumbled across Cassandra, we saw that Google have released a benchmark where they run 300 virtual machines in order to get 1 million IOPS. And it looks completely wrong. We come from deep roots in low-level programming in kernel space, and we worked on the KVM hypervisor project. And back in the days, that our recent KVM hypervisor job was about bringing 1.6 million IOPS with a single virtual machine. And that's kind of a different type of IOPS than a database IOP, but still it looks totally irrational. So that's the reason why we started the journey. And I'm happy to say that these days we do provide a database that on a single node can give you 1 million CQL, Cassandra query language operation per second, with great latency and all of the goodies of what Apache Cassandra delivers. So one slide about NoSQL. So NoSQL means that you'll trade off features, and the main two features that you're going to trade off is ACID consistency, so things are consistent but eventual, and also you'll usually waive joins in order to get way better performance, scalability, and high availability of fault tolerance. And most of those who picked Apache Cassandra pick it because it's the best framework out there until Scylla got to the space with regard to high availability. No other framework gives you distributed control over 1,000 machines, and it does it in a really good way with data center replication out of the box. So lots of good things, but at some costs. And I'll cover Cassandra for greater depth. So it's based on the Dynamo paper by Amazon. I heard rumor that Jeff Bezos was mad, furious, after the paper got published, probably without his consent. I guess with the success of these type of frameworks, he has a good reason to be pissed off, but at least the stock price, it's not reflected with the stock price. Maybe it's even good to have lots of hardware and to buy more AWS VMs. And also it's embraced good ideas coming from Google, and they also love you to use their hardware. It's written in Java, and it has a configurable replication. This configurable replication, how many people are familiar with Cassandra? So I won't bore you to death. Okay, it's like 50-60% of the audience, so I'll be quick about it. One of the things that you get for trivial working with Cassandra is you get to set any type of replication that you desire. Usually the number is 3, to have 3 local replicas and additional multi-data center replication that can get you to the level of, let's say you have 3 data centers, replication of 3 inside, you get replication of 9, so that's great for high availability. But the nice thing is that this configuration is totally tunable, so you can have replication of 1 for one table, replication of 10 for some other table. You can have consistency levels, so if your workload is read mostly, you can replicate the reads, but replicates all of the writes and just read from any node. And this way, you'll be able to get really good performance for your workloads. Some other infrastructure or databases don't get in near this configurable replication, and at best they have a single replica, and sometimes their architecture is not symmetric, so that they have different nodes with different roles, which is really hard to scale up. And if you have a failure, you need to test all of the different roles to make sure that if any of them failed, you won't have a single point of failures. And it's not the case with Cassandra. So I covered all that. Let's go on. So we touched a little bit that it's masterless, and all of the nodes are active-active. That's also an important good feature in Cassandra, and it has integrated support how to integrate data written by different nodes and make it eventual consistent. Now, one common misconcept is that when you have multiple data centers with Cassandra, it looks like this, where you have 2 rings or 4 rings or what's across your multiple data centers. And it's just a logical concept. Practically, there is one large ring, and it spans the entire cluster. And in a similar way that your local replicas get replicated, then also remote data centers get replication, but each time you add a node to any data center, then it gets a token range that belongs to the entire cluster. It's not a simple key value store. It's more for rich. It's even hard to say what's the exact model is, because there was a time where Cassandra used to be called column database, but it's not columnar, because columnar means that you'll keep the columnar compressed in your disk, and it's not the case. It's more for table, but each row is more complex than a standard row, and it can contain additional columns inside of it. And it's really good for time series data when you'd like to write a piece of data over time and later on grab a certain range and do different analytics with it. It uses a log structure merge tree approach for writing, updating, and deleting data. It's very fast for writes because you always append all of the changes to the database to additional files called SS tables, sorted string files, and it just gets accumulated over time. Even if you delete items, then the database writes a piece of data that calls tombstones. And later on, there is a background process called compaction, which tries to merge and delete duplications of data. One of the challenges of Cassandra and also for Scylla is to make sure that this background job is managed to run in a consistent manner over time, so data won't exceed what you have in your disk, or may not be the dominant factor and not get all of the bandwidth for your I/O processing. So that's a constant challenge that Cassandra has, and it actually suffers from. And in this talk, I'll explain how we're trying to tame the background processes. So together, to summarize the problems that exist in Cassandra, first, it's not utilizing all of your resources. And many times, it's almost impossible to get to a state where you get on a Cassandra box and you see 100% CPU utilization. You just don't get to see it. It's not just Cassandra, it's many other pieces of software don't do that to the level of that the average DevOps person thinks that if you have 100% utilization, maybe that something is wrong. But that's actually a good thing. You would need to consume the entire resources of your box. It's a good thing because this is what the hardware is for. And if you look at modern trend is to add more and more cores because the physics are basically, until there'll be a new discovery, CPU frequency cannot exceed from the number it is today. So Intel and the other competitors keep on adding cores, and modern software can't utilize these cores, and that's one of Cassandra problems. And I'll explain later on how we're squeezing all of the performance from the box. It doesn't necessarily mean that we'll be in 100% utilization all of the time. We are trying to be power friendly, but when there is load, we'll try to deal with it and to chew the incoming request or the background processes as fast as possible. Another problem with Cassandra is it's based on Java. We have no problem with Java. Let's take it off the table. We even wrote in our past an operating system special for running JVM workload. This is how we got familiar with the Cassandra project. However, it's not ideal for high-intensive I/O workloads. That's really bad. It suffers from memory allocation. It's against the trend. The memory amount keeps on rising. Amazon sells machines of 2 terabytes of RAM. And a common rule of the thumb is when you use JVM, do not use more than 16 gigs of RAM, 64 gigs of RAM, a really small amount of RAM comparing to what you can achieve with a modern system. So that's bad, and eventually if you use a large amount of RAM, then the JVM kicks in and needs to evict RAM with garbage collection, and you get to the situation of solve the world, which is bad, and that's why we chose the right tool for the job, which is C++. Another bad thing is tuning and configuration. not just Cassandra, it's again an industry problem where they throw on the user tons of knobs and expect the user to control and to be aware of so many knobs. I've been into Java 1 conference 2-3 years ago, and at the JVM tuning session, the guys said that normally when you have a really long line for controlling the JVM and the GC, it means that you have lots of parameters that cancel each other. It's really ridiculous, and it's not the way it used to be. Another example is with Docker and containers. Containers and resource groups were invented 10 years before Docker came along, but they were too complex. Only when Docker came along and simplified things, then it became consumable for the average user. And this is one of the things that we're trying to do. And last thing is, with Cassandra, it's really a challenge to do maintenance operations. One problem originates because Cassandra doesn't do a good SLA between background and foreground jobs. Another problem is because it doesn't utilize the whole box, then the trend is to use smaller and smaller machines because they don't get to use the large machines. But when you have dozens, hundreds, and even 1,000 machines in a single cluster, you'll naturally have a lot of hardware failures, like the MTBF didn't change of the hardware. And it means that you'll keep on need to administer your cluster and replace machines, and that's a big pain. So this is where we come in, and in one sentence you can think about us as the power and the richness of Cassandra at the speed of Redis. We actually have 2 users who switched from Redis to Scylla just due to performance. So we give you everything in a wave that Cassandra gives you with better performance. The reason I wave is, I'm an engineer that wants to be accurate, and so there are 3 features that are left behind and they're coming up later this year, and later this year we'll give you everything that Cassandra has to offer just with 10x performance. So today we give you the best highly available database, exactly like Cassandra, with multi-data center that works out of the box, with Spark support, with CQL, with automatic sharding, which is critical, and some other distributed databases don't have it out of the box. We even provide features that do not exist or aren't that great with Cassandra, like wide rows. Cassandra can store rows that are as big as 2 gigabytes. But if you have such a gigantic row and you access it, then you'll need to read from disk 2 gigabytes of data when you just need to modify or read just a tiny cell. So in our previous release, we added a wide row streaming feature that allows you just to stream the data that you need within a particular row. By the way, if there are questions, we'll have a longer Q&A afterwards, but don't wait up. Just you'll need to move away and speak from the mic, so the video and people remotely will hear. Before I'll dive into how we got to this implementation, last thing is the benchmark results. So we compared a YCSB workload against a cluster of 3 Scylla machines on Rackspace versus different sizes of Cassandra clusters from 3 to 30 nodes. These slides show the throughput performance. So 3 Cassandra machines did around 120,000 operations per second. That's the number, both the vertical AKIS and the horizontal, but this is the actual number that the Cassandra cluster managed to sustain. Our 3 machine cluster managed to go up to 550, a little bit less than the 30 Cassandra machines that we used. This is YCSB workload A, 50% updates, 50% reads. we tried out all of the workloads and also even a very large database, and the gap even grew further than the gap that I present here. Latency-wise, that's a 99 percentile latency. The 3 Scylla machines can be here where it's around 33% utilized. It's under 1 millisecond, and it goes to 5 milliseconds when it's 100% utilized. And even the 30 Cassandra machine cluster can't deal with it, and you see the latency number it provides you. And that's without even getting it through garbage collection stalls, which can be horrendous for performance and even for stability. So what's the magic? The magic is to tame puppies. In the sort of a taming, each puppy here represents a CPU, and beyond C++, another trick in the book we have is the thread per core or the shard per core that I'll provide details really soon, instead of standard threading. A few things before we dive into the implementation. So our administration philosophy is that everything's supposed to be self-tunable, and it may not be as great as I just tell you. There are things for us to do over time, but it's really is good and better than common other framework that you see, and Glauber will cover it with a couple of examples of how we relieve tuning not just the JVM, but also additional parameters, and trying to automatically understand what are the resources available for us. Another interesting thing is the high observability that we have using monitoring. Out of the box, we have collect-D monitoring, we have REST API, and also we added on top of it a JMX proxy that is there for compatibility with the Java management protocol. So with us, you can get 1 million operation with a 3-node cluster. The YCSB one is more richer in terms of columns, so performance varies with the number of columns that you have. You can deal with spikes. You can, one of the more not trivial things, but that we really recommend is to stop the way that you use caches across the board. Because first, you wouldn't, if you use Scylla, you wouldn't need to use that much caches, because Scylla is as fast as your cache, and it gives you great high availability and consistency. So drop your memcache and Redis, you can use Scylla directly. Another thing is use a richer model, not just key value, because many users use blobs and store them in Cassandra instead of using real data types and real columns. We suffer from a more complex data structure too, but we start with a better position, and eventually you get the benefit, and you reduce the number of lines of code that you write. In terms of compatibility with Cassandra, it's a drop-in replacement. It's compatible with the disk format, the SS tables, so you can shut down Cassandra and bring up Scylla. It's compatible with the configuration file, the Cassandra YAML file, the CQL language, of course, it's wire compatible, and that's why tools like Presto and Spark and the time series database and the graph database Titan just work out of the box. And you get to administrate the database the same way that you do with Cassandra, including backup and all the other routines. So how it works. What is that? Sorry? It's a drive, yeah. Modern generation don't know because there is cloud, and that's unknown. So I'm just checking that I'm here in the right venue. But it's possible to look at it as a drive, but it's also possible to look at it as a network device. And network device because you put data or try to read data, so you issue a request, And afterwards, a couple of microseconds afterwards, the request is available, and you get an interrupt that the data is there, and go ahead and read it. The reason that we try to think about it as a network device and not as a disk, because when you do work with network devices, then it's modern theme to work with asynchronous interfaces. When we work with a disk, many times not that much, and we work with synchronous mechanisms. But if you run on a CPU that is at least 1,000 times faster than your disk, and you work synchronously, then you waste time. Same thing when you work with additional cores alongside you, and you need to do that for locking, to access shared data structures. And also CPUs are network devices too, because there's a bus and the cores communicate. And if you lock something and try to access it, basically the entire bus is locked, and no other CPU, even if there's no lock contention, cannot use the bus to transfer data, and that's bad. So our design is mainly about everything is asynchronous, whether it's the network, the disk, cores, just memory isn't asynchronous. And we're trying to pull every trick in the book that we learned over the years and make it as fast as possible, including all of these components, and I'll cover that in the presentation soon. Scylla is an open source project, and it uses another open source project that we created, which is called Sistar, and that's the asynchronous engine in the heart of Scylla. So a lot of the functionality, the generic functionality built into Scylla came along with Sistar, and recently someone adopted Sistar and rewrote the Redis protocol with it and got really nice performance. We're trying to encourage vendors and the community to use Sistar directly. It's really good framework for a variety of things. Especially asynchronous and distributed computing, because think about it, when you work in a distributed environment, like a database with replicas, then when we get a request from a client, then we parse it and we start writing locally to the disk. And in parallel, we send requests to all of the replicas, both locally and also remotely for remote data centers. And the time that we can reply the client depends upon the configured replication factor. And it may vary between one table to the other. And it's really good to have a synchronous mechanism to ease the job of the programmer of writing this. And not to mention, it's very efficient. So let's cover additional design ideas that we implemented. So starting with the network and the shard per core notion. So here on the left-hand side, you have a traditional design coming from Cassandra, but it's not just Cassandra who has a similar design. It's many applications who are multi-threaded, have thread pool, and consume resources here in user space. The main caveat is that the kernel is the one that manages CPU, memory, I/O, and all of the other perspectives of a modern system. And the kernel is generic mechanism. It's unaware of the usage the application is trying to do. Sometimes it will try to guess what it tries to do. Sometimes the application will try to hint it, but it will never be optimal. And for instance, if a packet arrives on core number 10, then maybe the thread pool that will actually consume it will run on core number 20. And shifting cores between the two is super expensive. You'll have to lock the data. The CPU cache will get invalidated. Maybe the memory that the code is kept is on a different socket, and accessing memory that resides on a different socket is twice as expensive. So a lot of bad things happen. Instead, we took the shard per core approach. So we have two levels of sharding with Scylla. The first one is not that what you see here on the slide, is the cluster-wide sharding. We shard exactly the same as Cassandra. So we split a large data set which the cluster owns to independent nodes. But we have another level of sharding. That's what you can see here on the right-hand side, where we shard by per core. We shard the data per core, so each of the shards, it's totally transparent from the user. Each shard receives its own core of execution through a portion of the RAM. And this RAM is always local to the NUMA node. And it also may receive, if you have an advanced I/O network card in good disk, it may receive its own access to I/O resources. And it means that these shards are independent of each other, and you can scale up with your speed and the number of cores that you have in the system. So it's really efficient design, and when a client sends a request to one of the shards receives it, and it is the only shard that will process the request. It doesn't need to access some other shards, so we can run in a lock-free environment, and the data is always local to the shard. There are cases where a request spans across multiple shards, and if it's the case, we do it like a scatter-gather or map-reduced fashion, but in a specific way that we wrote, and we have SMP queuing mechanism to send the request and spread it to the other relevant cores. The cores do their own computation. No one is locking nothing because each shard owns its own piece, and later on, the shards signal the originator shards the request is ready, and it sends everything up back to the client. And when we started developing the database, we noticed we had an example Memcache project and an example HTTP project built with the Sistar technology, and we noticed that with Memcache, 90% of the CPU goes to the kernel for TCP/IP processing. And that's figures because Memcache is really simple application. It's not the Scylla code base, it's the Memcache code base that we started with it toying until we'll have a larger scope done. And since we discovered that, we decided to write our own TCP stack in userspace, which is also sharded according to the same principle that I provided, and we got 2x the performance with the Memcache implementation. This stack works with Scylla, but not yet fully integrated. There are a couple of low-level aspects that, in terms of integration, not in terms of usability, that aren't yet there. It's possible to use it, but it's not available to the audience, to the user community yet. It's available, but we don't recommend it yet. And it will come later on. And performance that I showed before is the standard Linux network interface. In the future, it will get improved once we'll use this DPDK-based TCP stack. It's better to use the mic if you have a question.
Does each shard have to have its own IP address?
No, they all live in one large process. So all of those shards are implemented in a separate thread. It's the same thread per core approach that many storage implementation uses, but it's extreme because it's not just the CPU, it's the memory, and Glauber will cover how we do memory allocation in this model. Good question. Another thing that we have is our own scheduler. We do use the Linux scheduler for scheduling threads, but each of our shards is executed by a single thread, at least concept-wise. And this shard needs to do different actions. It does its own compaction, its own repair, streaming, foreground processing, etc., etc. And that's why we needed a scheduler. So we have our own scheduler, which is built across very interesting design practice which is relatively common in the past years. It's called futures and promises. It's too low level for this session, but later on we can talk about it after the presentation. But it's super efficient. A single core can process million tiny tasks per second per core. So that's very valuable, and it's very lightweight as opposed as heavyweight threading mechanism, which is expensive in memory and also expensive in scheduling overhead. Another, I think it's almost ending my part, and that was the simple part. I'm kidding. So one important piece of that we provided to the disk or the block processing is the caching. Cassandra, for instance, and it's not the only one that utilizes the Linux page cache, and on top of it, there are application level caches like the row cache and the key cache that Cassandra had to move away from the heap because managing or using the JVM heap is even worse. So they have all of these structures. We just have one large unified cache. Usually we'll try to get a hold of the entire memory that is in the machine, but it's possible to also to tell us the amount of memory, whether it's 4 gig, 20 gig, half a terabyte, will work with what you've got. And that's it, no need to tune Scylla at all. Instead, it's pretty nightmare to tune Cassandra because you'll need to reserve enough memory for the Linux page cache, to reserve memory for the JVM, and reserve memory for these caches too. We're working right now with a vendor that is about to provide a reference architecture and to compare Scylla and Cassandra. And their main challenge is to tune Cassandra to the way that it'll be fair to show a comparison. And it's really hard to do. But beyond tuning, which is hard, then there's the notion of efficiency of memory usage. If you use the Linux page cache, then you cache with 4K bytes granularity. And if your object weighs just 300 bytes, then you just waste all of this memory, which is a shame. So instead, we work with the object level, so we don't need to do that too. And last thing is, doesn't go back. Last thing is if data isn't in the cache, then you get a page fault in the Cassandra case. And the problem is that Cassandra is unaware that data isn't in the page cache. So when Cassandra accesses a piece of data, then it hits a page fault. And when it hits a page fault, then the kernel deschedules the running thread and halts it, and it schedules some other context like the IO constant, and which does the DMA from the kernel, and later on it schedules some other thread to run in between, and that's here, so you don't even get to see that. And later on, when the data is ready, then they signal the calling context and they schedule this thread back again. So you suffer both overhead and a lot of latency. What we do is we were aware that the data isn't in the cache, so we schedule the DMA directly to the disk. We use ODirect, so it bypasses the Linux page cache. And since we have our own scheduler, once the data arrives from the disk, we go and run this tiny task, which we can do million of them per second per core. This presentation actually mimics exactly how we were a year ago. A year ago, we went out of stealth mode, presented our beta at the Cassandra Summit, it was great. We started to get traction, but along that time, we didn't know a lot of things. So we knew how to write super fast and efficient software, but power isn't that just there without control, and especially in a distributed framework, which you have a lot of nodes, you have failures, you have a lot of challenges. And I think that over the course of the past year, we try to improve and address all of these cases and make the database sing when it's hard, or sing when you need to stream data to other nodes and you have failures. And this part will be done by Glauber. We call this set of algorithms workload conditioning, because we're trying to automatically manage the resources to the best way possible.
Thank you, Dor. I hope you can all hear me. If not, I'm supposed to kill that guy. Can you hear me now? He's like fighting for his life. You can see that. So, as Dor said, I'll be talking about workload conditioning, which really is an umbrella term that we have been using for various things we have been implementing in Scylla, and we'll keep doing it. So workload conditioning is not a feature that will ever be ready, but on the other hand, it is a little bit, or you can think of it as part of our philosophy of how things should be done and are done in Scylla. The main idea is that we have information, we are the database, we are processing our requests, and we know exactly what's going on inside the database. If we don't know, who does? Nobody. And we can use that information to insert various feedback loops, like feedback control loops, and act on those. So I'll give some examples and hope it will become clearer. So as I said, those are the main commitments that we have in Scylla, which is like improve your performance, improve your latency, and keep compatibility with the ecosystem at the tooling level, so you can reuse your application, you can leverage on the infrastructure you already have. And not only when we talk about performance, we not only want to save your hardware resources, but also your human resources, the amount of time you put into managing this thing. This graph that you see here is the response of an SSD to increasing number of requests. So SSDs, modern hard drives, are known to be very parallel. But how parallel? That depends a lot on the disk. So what you see here is as you ramp up the number of requests, your performance gets better. So I'm looking at the numbers, and you start something like 50,000 IOPS, and then you climb it up to 150, 200,000 IO operations per second. At some point, like those requests are all in parallel, so you get parallelism. At some point, that stops. At some point, all you see is your latency going up, but you're not getting more requests out of it, right? So this is the basic problem. This is the core. This is at the very core of what we do. We notice this and say, okay, so if we have a lot of resources that we do, as Dor mentioned, our CPU model is very efficient. So we can throw, looking from the disk perspective, most of the time like an infinite number of requests into the disk. But if we throw more than that, this is not going to do it any good. So what we do instead, let's see if I got this right. Yeah. What we do instead, we queue those resources ourselves. So those requests are all in the database. They're not sent to the disk. We only send this amount of requests that you see here. In this case, for this particular disk, about 150. And if you one of you already run Scylla, if any of you had already had the opportunity of running Scylla, we ask you to run that tool Scylla IO setup beforehand. That's what it does. It's basically trying to gauge your disk and push requests and figure out what is the best number of requests for your disk to operate within. So a normal stack, like a normal software, normal piece of software that is not aware of those issues or doesn't necessarily care about those issues, We'll just push requests into the file system. They go to the block layer. Eventually, at some point in the future, one would hope they would reach the disk, be it a single disk or a disk array. What Scylla does instead, through the Sistar project, is we have our own disk I/O scheduler in userspace that we wrote, and it's part of the Sistar project. And then if we know there are more requests outstanding than that number, we just don't send them. We queue them and we wait. And one of the things that we can do is, first of all, make sure that the disk is always operating in the sweet spot. The disk is never overloaded. If you overload the disk, a host of problems actually happen. So we prevent those problems. Our performance gets better just because we do that. But on top of that, each one of those classes, like which basically means where is I/O coming from, they have their own queues, and we can measure the size of this queue. And then we say, okay, so there are a lot of requests that are coming in from memtable writes. And not that many requests for compaction. So, maybe we should prioritize this instead of that. Then we can play with those priorities to make sure that you don't have to tune your system, because we know the distribution of requests into the disk and to other parts of the system as well. So this is the current, more or less, the very up-to-date figure of what we do in this userspace I/O scheduler. We have one class for queries. So when you do a SQL query, and you don't need to worry, oh, maybe your disk is totally overloaded. You say, oh my God, I'm running at a 100% disk utilization, but I want to query my database. Will I be able to? Yes, because when I get this request, I say, okay, here's a request for query, and queries are not really getting a lot of attention from the disk, so we just do not send the other requests are queued. They're not sent to the disk. We're just queuing them. So this query request comes in, all right, time to go, and then that executes. Same thing for the commit logs. So when you're getting requests that are coming in, you need to write them to a commit log. So we know exactly how many requests, at which rate they're completing. We know all of that. Compaction. So when we do compaction, pretty much one of the complaints that a lot of people run into Cassandra, hey, my compactions are either too slow or too fast. And then what you need to do is you need to set a threshold. You said, okay, I go and measure empirically, say that maybe you shouldn't do more than 5, 10 compactions in parallel. Anything changes in your hardware, and then this number out of a sudden is not good anymore. Not with us, not with Scylla. In our philosophy, what we try to do through the I/O scheduler is, okay, awesome. So we know exactly how many requests the compaction should be having for you to have the best performance possible out of your system. Same thing with streaming, same thing with flushes, same thing with whatever we need to do. Now, what I'm going to show you is basically one example of this in practice. We have a fairly small server, and this deviates a little bit from the benchmarks we usually show, which is why I'm showing it, which are like very big machines processing a lot of requests. And sometimes people ask, okay, well, what about if I don't have it? If my machine is very small, is it still worth it? I mean, is Scylla still any good? For this workload, then, it's a very small server. This is all running on Amazon. It's not on-prem, so it's like not the best hardware in the world. And each row is about 400K in size, 400 kilobytes in size. So they're fairly large as far as this Cassandra rows goes, which makes a very challenging workload for the disk. The disk is going to work a lot. And again, those disks for this very small instance, they're not exactly very fast. Sorry. So we have a populate phase 1, and I just write 200,000 partitions into that server. And once this is done, just wait a little bit for it to keys, and have two very large clients. So now the clients are much, much more powerful than the server. And one of them is going to be writing at full speed, a different set of keys, and the first one is going to be reading the first set of keys at full speed. And I'm going to show you what happens with the memtable writes, with the compaction, with the query, and the commit log classes. And this is it. So you can see like those graphs are to scale. The first graph on the very top, what you see is the number of requests. So yes, it's not perfect just because the hardware it has fluctuations, but pretty steady workloads. I mean, reads and writes at the same time. So you can clearly see the first phase here is populate. The second phase, reads and writes at the same time. And the bandwidth that the query class gets, it's pretty much the same bandwidth that the commit log class gets. Compaction gets a little bit more because we figure, like one of the things, it's not it's not enough to get more bandwidth to the query class if you're not reading fast enough, because you might be reading a lot because you have a lot of SS tables. Then we're better off just compacting them. Like, we take all of that into account. You can see your mem table flushes, again, pretty much to the extent that the hardware allows, flat line. And we managed to keep the bandwidth pretty steady given the request rate, and manage them. You can see, especially like the query and the writes, they're at the same level. They get exactly, especially because this workload is like one server each, a very fair amount of bandwidth. Now, we control that. Flat line, yeah, we know that. Now, this is another example. Though this is a little bit more challenging in the sense that the previous example was a single node, just so you can see things like it's not necessarily from, that doesn't have to, this works in a cluster. So of course, if you're running Cassandra, Scylla, you want to see it working on a cluster. So those are 6 machines, and the compactions go up in time, which is expected. Like, this is a write-only workload, so you don't have reads in here. And I'm just seeing results from the 6 servers at the same time. And those are bigger machines. Those are Amazon as well, but the bigger machine they have, like and this is something like almost 100 clients. Again, you can see that the bandwidth is very steady, very stable, and we are totally in control of that bandwidth usage. Now, in this figure, a little bit more about how our memory is managed. We have 2 memory allocators within Scylla. The first one is what we call the standard memory allocator that we use for pretty much anything that it doesn't use the other allocator. That's the standard definition of standard. Like, it's used by anything that is not non-standard. So it's still not the glibc allocator. It's still not like your usual malloc that you do in your application. It's our allocator that we wrote it, and everything that it allocates in a CPU is freed in that CPU. When I work with the Linux kernel, which I did for more than a decade, one of the main problems we had in the memory allocators was exactly this. I mean, I'm allocating in a CPU. If I free in that CPU, that's the hot path. That's great. That's fast. But if I'm freeing from a different CPU, it's very slow, because you need to lock, you need to wait, you need to do a lot of stuff like that. In Scylla, this choice does not even exist. If you allocate here, you're free here. But other than that, the interface is just the same. It's malloc, is free, is the new, delete, pretty standard C++ stuff. And alongside with that, we have a log structure allocator. And that basically, what it means is that it's a compacting allocator. So it will move the objects around. It does something fairly similar to what a garbage collector does, except that we are in total control, again, on when it runs, for how long it runs, and we know where all of the objects are. We don't need to sweep this, and we use this for some of our allocations that need to be, that we understand that they need this flexibility. Those are the mem tables, which are the staging area for things that are written to the database, but they're not yet in disk, and the cache that Dor mentioned, that it's our unified cache in which everything lives. And of course, whatever is not one of those is free memory. With those in mind, like how we do, I'll give you one example of workload conditioning. The kind of stuff that we do to make you stop worrying about tuning your database altogether. Those are internal feedback loops, as I said. So we pay attention to what's going on. We know the size of each of those pools. We know how big your memory is getting. We know how many requests are being pushed to each of those classes to the disk, how many requests are coming back. Knowing all of that, we can do things like this. So we have the Sistar scheduler, which is, again, part of Scylla. And when I say scheduler here, is the disk scheduler, the CPU scheduler, and the upcoming network scheduler. We don't have that one yet, but this is for the future. And all of the classes, like the commit log, the mem table, compaction, whatever we need to balance within the database. And the compaction backlog monitor is actually not fully completed, but they're all things that will be coming very soon. As I said, this is not ever something that we will finish. We're always trying to find more stuff that we can do ourselves to relieve you from tuning. But when we see, for instance, that the idea is that, okay, I have a lot of compactions, and the compactions are pending. They're not completing in time. So what can I do? I can come to the scheduler and say, give more priority to compaction. And what will happen at this moment is that your load will run a little bit slower for the time being, so that compactions can keep up. And when they reach equilibrium again, say, awesome, cool. Then everything fits into this equilibrium point. We do the same thing for memory. So you're using a lot of memory. That probably means that we're not being able to, your disk is not as fast. If your disk is not as fast, I cannot keep accepting requests from you that fast. I need to be a little bit slower. And when we do things like that with Cassandra, for instance, what you do is again, throttling. You just say, okay, well, the maximum amount of memory is this much. You should never use more than 2 gigs for mem tables, but this is empirical. It only works for this workload that you have measured. And for us, again, we try to juggle those things and figure out by ourselves what are those sweet spots. So again, same thing, we can adjust priority. We can say, all right, so the mem tables are not getting the attention that they need. Give them more until you reach an equilibrium point. And this is done through a series of feedback loops. That's pretty much what it is. Again, just so you refresh your memory, here's the figure. Now, the example I'm going to give you is exactly this one I've been hovering over. It's a case in which the disk is not fast enough. So that you have your CPU, I don't mean to say that the disk is slow, it's just that it's slower than the CPU. So it's much, much slower than the CPU. So your CPU is a lot faster. If you just keep accepting and acknowledging requests, when you write to memory, to commit log, to mem table, at some point your disk will not be able to keep up. So that's just physics. It's not any implementation detail. So what happened is that we look at this memory. We know how much memory we have. How? Because we know. Like everybody knows. We just have all the memory that you assign to Scylla. So we know, whatever. The whole memory in the box, 1 terabyte, 16 gigabytes, and either all of memory, or if you told us a number, never use it for Scylla more than 20 gigabytes. Those are like 20 gigabytes. Technically, if everything goes well, as I'm receiving those requests, if you're familiar with the Cassandra model, I'll act the requests as they are in the memory buffer. We do the same. And at some point in the future, I will write them to the disk. They will accumulate in the mem table and will be written to the disk. This is not supposed to reach half of your memory. If it does, it means I'm not actually flushing fast enough. And if I'm not flushing fast enough, I just stop accepting requests. I don't accept requests from you anymore. Sorry. Until when? Until I manage to free 1 byte. Until I manage to write 1 byte to the disk. When I manage to write 1 byte to the disk, I can accept 1 byte of your request. So when I do that, I know that I'm now accepting requests exactly at the speed that the disk can handle. And of course, in reality, it's not that I never write 1 byte. I write, of course, a buffer that has, let's say, 128K bytes. And then I say, okay, now I'm good to go for more 128K worth of resources. And if I do that, again, for every request that is written, every piece of memory, every byte that is written, I accept the exact same amount of memory into new requests. Basically what I have done is I brought your system from memory speed to disk speed. And now you will not choke. You will run at the speed that your disk can handle. And this is basically one example. Like the graph in the top is basically how it works internally. I'm not going to spend too much time on it. I will focus on the one on the bottom. So what happens here is you're getting like 8K requests. And it's not a very challenging workload, but a very slow disk. And we're fine with that, but until at some point when we reach the threshold, when the yellow line, which is this dirty memory, keeps growing and growing and growing, and it reaches the point that says, okay, this is half the memory, I start accepting requests only at that rate. And what you have after that is, again, pretty much almost a flat line that is basically fluctuating as much as the disk fluctuates. So I brought your system from the memory speed, CPU speed, to disk speed, and you have done nothing about it. Like you didn't have to measure it yourself, you didn't have to tune it, you didn't have to write in a configuration file, throttle at 3,000 requests, you didn't have to establish a maximum or anything like that. This is just a feedback loop that you saw in the previous slide. Again, the disk cannot keep up. I cannot sustain this rate. I mean, I can, but then I won't be able to write it to disk. Memory can handle, CPU can handle, the disk can't. Then after that, the workload conditioning will figure out what is the ideal, the best request rate for your cluster. In this case, it's not a cluster, just to keep it simple. It's actually only choose CPUs out of the machine. But after that, all right, flat rate, pretty much flat line. This is the ideal request rate. If you were to throttle your clients, that would be the rate. You would have to write it down. We did it for you. As I said, workload conditioning is not something that will ever be ready. It's not a feature that we're working on and we'll finish next month. This is part of Scylla's philosophy. So some things are ready, some things are not, some things we haven't even thought about. Some things are things that are still like researching. If we put those two things together, as I said, like the disk shares, the fact that we can play with how much of a priority each of the classes have, and the memory, one of the things I can do is I can actually go and modify those shares. Right now, those shares are static. You could see like they get more or less the same bandwidth, like for the classes that have the same number of shares. We can modify this. We can look and say, okay, so maybe memory, I mean, the disk is not being able to keep up, but the other classes are not important right now. You're not getting as many read requests, so just move more shares to this class and the overall performance will be better. So this is something that we still should do. Another example, now how big should a mem table be? This is part of the configuration file in Cassandra. If you go to Cassandra, the default is something like 11% of the memory. Now who came up with that number? What is 11%? And it's probably a lot of measurements. Why 11? If you watch the Stranger Things, you say, oh, 11 because I love 11, like as the main character and she's great. But again, in real life, that doesn't have to be this way. And in our case, we will just, that's actually an upcoming series of patches that are almost there, almost ready. We just do away with this number altogether. You don't have to configure in your file how big your mem table should be. We'll just figure that out based on all the things that are happening in the system at the same time. So again, depending on the disk speed, depending on the request rate, we figure this out, and when we feel it's time to flush your mem table, we do it. You don't worry about it. That's, again, part of our philosophy. Things that are coming soon. Repairs. Repairs, again, big pain point for people using Cassandra or other technologies for that matter. One of the things we have done in previous versions is that repair was, and some people set it like as sluggish as slow, so it does not affect the load. So right now we can make sure that requests will not dominate the CPU, will not dominate the disk, especially through the I/O scheduler. We have we can guarantee that your requests will not slow down too much. Of course, if you're running at a 100% everything and a repair starts, you slow down a little bit, but we control how much. But there are things that we can do in repair to make sure that it goes faster when other things, basically by adjusting those shares and saying, okay, so right now it's better if I just get your request to be even at a lower rate for 5 minutes, whatever, just so the repair can finish, and then we readjust those things later. So this is upcoming. We'll make sure the repairs will go faster when they can and they should go faster. We'll be looking at the size of the backlog to do that. So as you can see, we do have a framework for us to do those things. Those are things that are real. They exist right now. We have the basic framework, and over time, we're getting more and more things into this tree, into this umbrella, using the same backbone, the same technology, just getting more things done. Again, another thing, if a new node joins the cluster, one of the things that happens, what happens when a new node just booted and joined the cluster with stale data that it has? Maybe this node was down and now it's up again because you took it for maintenance or whatever. The cache is cold. It's reading all of the data from disk while the other nodes are serving at least part of those requests, maybe if you're lucky, all of those requests from memory, from cache. So this node is going to be a lot slower. Now, one of the things we can do, we know that. And we know the request, we know the node just joined. We have this information. There are no variables in that equation for us. Everything is known. So basically the coordinator do not send requests to that node. Well, not at first, it sends some requests, maybe 10%, and give this node time to warm up its cache up until the point you realize, okay, this node is now as fast as all of the others. Now we can get as many requests as the other nodes are getting.